Okay, so in today's tutorial, we are going to discuss the atomic structure, okay, and chemical bonding, okay. So to start our tutorial, let's understand some few terms. The first thing you need to understand is what matter is, okay. So matter is defined as anything that occupies space and it has weight, okay. That is what matter is, okay. We can also have elements. Elements are simply substance, okay, that cannot be separated by any chemical means. And these are stable substances, okay. And these elements are a form of matter, okay. So that's what you're having. That's another term you need to know. Okay, so we have different examples of elements. You have a lot of elements like oxygen, nitrogen, and chloride there. Okay, so these are elements. Now, if we get these elements, we put them together, we form what we call molecules. Okay, then these elements, they will have a small basic unit in them, and that basic unit is actually going to be called an atom. Okay, so that's what we have. Okay, so now we are saying we can actually combine these elements physically. Okay, so we can combine them physically to form mixtures. Okay, so we can combine elements physically to form mixtures. Then we can combine these elements chemically to form compounds. Okay, so that's what we have. Okay, okay, so a compound is simply a chemical combination of elements that has its own set of properties and a defined composition. Okay, so compound, how they are formed, we get an element, can be one element or more elements. We put them together, we're actually forming a compound. Okay, so now here you can see the examples of compounds we have in here. So you can get your sodium and chloride there, okay. We put them together, we form sodium chloride as a compound, okay. We can have water is also a compound there, and HCl is also a compound, okay. So all these are formed by the combination of elements, and we are talking about chemical combination of elements, and we are getting these compounds, okay. So that's what we have. Okay. So now there elements and compounds are the two types of substances, often referred to what pure substances. Okay. So now, if you look at the structure of an atom, okay, the structure of an atom itself, let me just go here. It will be composed of three particles. Okay. So you have three particles of an atom. Okay. So the first one is going to be a proton. You can have the neutron and the electron. These are the three particles of an atom. Okay. So now, if we look at the atom itself, you notice that it will have other parts. It will have the nucleus and the shells surrounding this atom. Okay. So in this nucleus, in the nucleus of an atom, that's where we find two particles, and these particles are going to be the protons and the neutrons. Okay, so the protons and the neutrons are going to be found in the nucleus there. Okay, then in the shells, you are going to find electrons. Okay, so if we are to view the properties of these particles, you notice that electrons are actually negatively charged. And in terms of weight, these electrons have a very small mass that they are considered to be negligible. Okay, so these guys are negligible. They have no weight. Okay, because their mass is very small. Okay, then you notice that the mass of the protons and the mass of the neutrons, they are about 1 atomic mass unit. Okay, so meaning the entire weight of the element is dependent on the nucleus, where the protons and the neutrons are located. Okay, so here that's where the entire weight of an element is going to be dependent on. Okay, so you notice that these electrons are actually negligible. They don't have any weight. Okay, so those are some of the things you need to know about the atomic structure. Okay, so now in that atomic structure, you actually have subatomic particles. Okay, so you can have the Fermi Dirac distribution function, also called the Fermi function. So this one provides the probability of occupants of energy levels by fermions. Okay, so when we talk about energy levels, okay, so these shells are also energy levels. Okay, so these are actually these electrons which are in the shells. We don't know exactly the position where these electrons are located. Okay, so now the probability of us finding these electrons in the energy level is what we call the Fermi function. Okay, so that's what we have. So if in terms of those particles, the fermions, okay, so they are actually half integers. They are half spine. Okay, so you find that in this energy level, you actually have orbitals. Orbitals is where these particles, the electrons, are going to be found. And these particles are going to be half spined. You find that one is going to be facing up and the other one is going to be facing down like that. Okay, so that's what we have. And we are saying the probability of us finding these electrons in an energy level is what we call the Fermi function. Okay, so that's what we have. Okay, so we also have what we call the Bose instant statistics. Okay, so these ones will apply only to those particles not limited to single occupants of the same state. Okay, so that is particles that do not have that do not obey the Pauli exclusion principle restricted. We'll talk about this guy as we are moving. Okay. Okay, so this is what we are talking about. So in this, we are going to find protons and neutrons. Then you are going to find electrons that are going to be located in the shells. Okay, like that. Okay, so these are actually energy levels. And then these are electrons, and these electrons are going to be found in a space called an orbital. So we are going to find these electrons in an orbital. Okay. Okay, so in terms of the sub atoms, you can have what we call the quarks. Okay, so for the quarks, for the protons and the neutrons, simple, straightforward. Okay, so for protons, you have two quarks up. Okay, and then you have one quark down. Okay, then for the neutrons, you have one quark up, the opposite of the protons, and then you find that you are going to have two quark downs. Okay, so that's the other property you need to know about these subatomic particles. Okay, so now we made mention of shells, subshells, and orbitals. Okay, so so it is important to understand the location of the electrons. So we are saying electrons do not move freely in the space around the nucleus, but are confined to region of space are called shells. Okay, so we are going to find these electrons which are going to be located in shells, but we will not know the exact position where those electrons are going to be. Okay, so we are just getting the probability of us finding that electron in that energy level, the shells. Okay, so now each shell can contain up to 2n2 electrons. Okay, so for the first one, so for the first energy level, you can have 2, you can put 1 there to the power 2. That is 2 times 1 there, okay, which is 2. So meaning in the first energy level, we are going to have 2 electrons. In the second one, we are going to have 2 to the power 2, okay, like that. So we are going to end up having 2 times 4 there, which is 8. So in the next energy level, we are going to find 8 electrons. Okay, so that's what we have. Okay, so each shell contains subshell known as atomic orbitals. So in these shells, so we are saying these are shells. So we have the nucleus, then we are going to have shells surrounding this nucleus, okay, where we are going to find electrons. Now, in these shells, there is actually what we call subshells. Those subshells are also known as the orbitals, okay? So in these orbitals, that's where actually these electrons are going to be located. So your electrons, you are going to find them in these orbitals. That's where you're going to find the electrons there. Okay, so in each shell, we are going to have orbitals. And what you need to know about these orbitals, one orbital can occupy a maximum of 2 electrons. Okay, so one orbital can occupy a maximum of 2 electrons. That's what we have there. Okay. Okay, so now we have different types of orbitals. We can have the s orbital, which will have a spherical shape, okay, looking like this, okay. You can have the p orbital, p orbital, okay. So in terms of the p subshell, is going to be composed of 3 orbitals, okay. So you can have the two, you can have the px, you can have the py, you can have the pz, okay. So that's with the p orbital, okay. So you are also going to have the d, which is going to have which is going to have the d subshell is going to have about 5 orbitals, okay. So you're going to find 5 orbitals for the d subshell. Then you have the f subshell, the g subshell, and so on and so forth. So these are some of the subshells that you are going to discuss in this course. Okay. Okay. So now we also need to understand about electronic configuration. Okay. So let me just do this. Okay. So we also need to know electronic configuration. Now we've discussed subshell orbitals, and we are saying these orbitals, that's where electrons are found. And we are saying in each orbital, in one orbital, you are going to find 2 electrons. Okay. So now you need to know how to write the electronic configuration using orbitals. Okay. So you need to follow this arrangement when coming up with the electronic configuration. Okay. So the first thing, you need to start with the lowest energy level. So when putting electrons, you start with the lowest energy level. So for example, the lowest energy level you're going to have is the 1s, okay? From the 1s, you go to the 2s, then you go to the 2p. From the 2p, you're going to go to the 3s, okay? Then you go to the 3p, then you go to the 3d, like this, okay? Then from the 3d, you go to the 4s, okay? Then you have the 4p, then you are going to have the 4d, then you are going to have the 4f, like that. Okay, so that's how we are going to move in terms of the energy levels, starting from the lowest going to the highest. Okay, so you can have the 5s there, you can have the 5p, you can have the 5d, 5f, then 5g, in that arrangement. That's what you have. So this is the arrangement you need to know when arranging your electrons in orbitals. Okay, so for example, let's say they tell us to find the electron configuration for carbon. Okay, so the electron configuration for carbon is going to look like this. So the first energy level is the 1s, and we are saying in each orbital, we are going to find 2 electrons, and the s orbital, the s subshell has actually 1 orbital. Okay, so since there is 1 orbital, meaning this one s can only have 2 electrons, so you're going to put 2 electrons. We know that carbon has 6 electrons. Okay, so we are going to put 2 electrons there. Okay, then from there we go to the second energy level. So in terms of movement, we'll be moving like this. Okay, so that's how we are going to be moving, like that. Okay, so you need to follow that arrangement. Okay, so from the 1s, we go to the 2s there. Okay, so with the 2s, you're going to have 2 electrons as well. Since it's the s subshell, you're going to have 2 electrons as well. Then from the 2s, you go to the 2p there. You can see from here, you go to the 2p. Okay, so in the 2p, the p orbital, the p subshell has 3 orbitals. we've discussed the three orbitals which are in the p, which is the px, the py, and the pz. Okay, so meaning this guy has three orbitals, and we are saying these three orbitals, each orbital can occupy 2 electrons. So we can have 2 electrons there. Okay, so we're going to have 2 electrons which have remained from the 6. Because here we have 2 plus 2 plus 2, which is 6 there. Okay, so this is the electron configuration for carbon. So you need to know how to come up with the electronic configuration for your subshells. Okay, then the other thing you need to know is about the valency. Okay, so here what you need to know, the valency is something that tells you how many electrons are going to take part in a chemical bond. Okay, so you find that this valence is actually going to tell you how many electrons you are going to lose or how many electrons you are going to gain. That's what we have. Okay, so in terms of valence electrons, those are the electrons that will actually participate in a chemical bond. Okay, these are the electrons that are going to be found in the outermost shell. Okay, so if we do our electron configuration like this one, you know that the first 2 electrons, these ones, they are in the first energy level. Okay, so these one are actually the core electrons. These are called the core electrons. They are inside the energy level. These ones do not participate in a chemical reaction. Now, these which have remained, you find that these ones are going to be found in the outermost shell. And these are the electrons that will actually participate in a chemical reaction. These are what we call the valency electron. Okay, so that's what we have. Okay, so are we clear up to here before we bring in some new concept? Are we clear on the valency, the atomic structure, and everything? Okay, so that's what we have. So we also have what we call ionization energy. Okay, so this is the quantity of energy that an isolated gaseous atom in the ground electron state must obtain to discharge an electron. Okay, so when we talk about ionization energy, we are simply talking about the amount of energy you need for you to move an electron from a subshell. That's what ionization energy is. Okay, so you will notice that as the atom increase in radius size, or we say in radius, we are talking about the size. So as an atom increases in size, which is radius, you notice that ionization energy also reduces in that case. Okay, so you notice that as the radius of an atom increases, you will find that atom will be far away from the nucleus. Okay, so you find that it will be easy for you to remove the electrons, the electron which is far away from the nucleus compared to the one which is closer to the nucleus. Okay, so if we are to follow the trend in the periodic table in terms of radius, the radius of atoms, you notice that as you are going down the group, the radius of atoms usually increases. Okay, then you also have your ionization energy, which is also going to increase, which is going to decrease. Okay, so as you are moving down the group, the ionization energy is going to decrease because the size of the atom is becoming big. The atomic radius becoming big. Okay, so you notice that the one in the first period, if you check your elements in the first period, they are going to have smaller, they are going to be small in size compared to the electrons, they say, in the period, in period 6. So as you are going down the group, you find that atomic radius increases, then ionization energy reduces. Okay, then as you are moving from this side to the other side, okay, from your left to your right, you notice that in terms of the radius also increases as you are moving from your left to your right. So meaning ionization energy also decreases as you are moving from left to right? Okay, so that's another thing you need to know about these particles of an atom. Okay. Okay, so this is about the electron configuration, which we've already discussed. Okay, so we are saying the first energy level, the lowest energy level is going to be the 1s, followed by the 2s, you go to the 2p, the 3s, 2p, then you go to the 4s. Okay, so you follow this arrangement. Okay, so you start with the 1s, then you go to the 2s, then you are going to the 2p. Okay, then from the 2p, you go to the 3s, go to the 3p, then you're going to the 3d. Okay, then you go to the 4s, 4p, then 4d. Okay, then that's how the energies are moving here. So you move like this. Okay, that's how you move. So you always start from the lowest energy level. As you can see, this is the orbital diagram showing how the electrons are going to put, starting from the lowest energy level, which is the 1s, going up there, the 3d, which is the highest energy level. Okay, so that's what we have. Okay, so for example, here we have been given Fe with atomic number of 26. Okay, so meaning how we are supposed to put electrons. So since our atomic number is 26, and we know that for a normal atom, okay, the valence, the number of electrons are actually equal to the proton number. So if the proton number is 26, even the electron number is actually 26 in that case. Okay, so if we are to like to come up with the electron configuration, we'll follow our arrangement. You start with the 1s, which is the lowest energy level. You go to the 2s, and remember for the s orbital, it will have for the s subshell, it will have 1 orbital. For the p subshell, it will have 3 orbitals. Then for the d, it will have 5 orbitals, like that. Okay, so meaning you have to take this in, you have to consider this as well. And you notice that in the S, you have 1 orbital, meaning only 2 electrons can be occupied in the S. Then in the P, you are going to have 3 orbitals, meaning about 6 electrons can be occupied in the P, isn't it? So you are finding 2 in each orbital there, 2 in each orbital. Okay, so meaning you can have 6 electrons in the p subfield here. Okay, for the d you can have 10 because you are going to be having 2 in each as well. Okay, so meaning 1s there you're getting 2 electrons, then 2s you are also getting 2 electrons, 2p, so p you have 6 electrons there, then 2s 2 electrons as well there. Okay, so make sure when you come up with the electron configuration, when you add those numbers on top, these ones should be able to get 26. Okay, so that's what we have in terms of electron configuration. Are we clear? Are we able to come up with the electron configuration if we are asked? Are we clear here on electron configuration? Is there a question? Make sure you ask if there's no question. These are the things you are going to find in your test one. So are we clear here? Or now we come up with the electron configuration for different atoms. Okay, so if all is well, we can move. Okay, so we can now talk about quantum numbers. Okay, so some of these things are the things you've done in the first semester, but I'm just trying to remind you. Okay, so we have about 4 types of quantum numbers. We can have what we call principal quantum number, angular momentum quantum number. We can have magnetic quantum number and what we call electron spin quantum number. Okay, so let's discuss these quantum numbers one by one. Okay, so let's start with the first one, which is the principal quantum number. The principal quantum number is denoted by letter N. What does it tell us? The principal quantum number. Okay, so the principal quantum number simply talks about the energy level or the shell where you're going to find your electron. Okay, so the N is simply for the energy level or the shell. Okay. So you can have different types of shell. The first shell is the K, the L, the second one. The fourth one is the M. These are just numbers for different subshell. You don't need to know them. Okay. So the first one is actually known as the K, the L. You can have the M for the third one, and so on and so forth. Okay. So that's what we have. Then we can have what we call angular momentum quantum number. Okay. So for angular momentum quantum number, simply tells us the shape of orbitals. Okay, so you can have the s orbital, you can have the p orbital, the d orbital, and the f orbital. Okay, so now one thing you need to know about this angular momentum quantum number. So it's donated by letter L. So if at all you are given the principal quantum number, okay, so let's say they are saying our n is equal to 2, okay, we can actually find the L, which is the angular momentum quantum number, okay. So we actually follow a formula n minus 1, okay. So this n simply means the principal quantum number, okay. So in this case, let's say if n is 2, meaning the energy level is 2, meaning our L is going to be 2 minus 1, which is going to be 1 there. Okay, so meaning your angular momentum quantum number is going to be 1. Okay, and what this means, if your angular momentum quantum number is 0, that means that the type of orbital you're going to have is the s orbital. If it's 1, you're going to have the way we have in here, meaning you have the p orbital. Okay, if it's 2, you're going to have the d orbital. If it's 3, you are going to have the f orbital. That's what this angular momentum quantum number means. Okay, so that's what we have there. I hope everything is clear. We can also have what we call the magnetic quantum number. Okay, so for magnetic quantum number, okay, so magnetic quantum number simply tells us the orientation of these orbitals. Okay, so you can have okay, so this simply tells us the orientation of our orbitals. Okay, so for example, if our L, let's start with our L. If our L is 1, the way we've found the previous one, we are saying if n is 2, okay, then L is 1, meaning the type of orbital we are having is a p orbital. Okay, and then ML, which is the magnetic quantum number, tells us the orientation of these orbitals. Okay, so here the orientation, if your L is 1, the orientation is going to be +1, okay, 0. Then you can have, okay, sorry, let me start with minus. Okay, so the orientation can be, so you start with -1, you have 0, then you're going to have +1. So this is your ML if your L is 1. Okay, if your L is 3, let's say if your L is 3, or let's say N is 4, meaning our L is 3, isn't it? Using our formula, since we are saying L is equal to N minus 1, then we put a 3 there. We are going to get, we put a 4. So we are saying N is 4. We are going to get L3. So if L is 3, ML is going to be -3, -2, -1, 0, +1, +2, +3. That's the orientation. Okay. Then the last type of the quantum number is what we call the spine quantum number. Okay. So for the spine, it's donated by MS. Okay. So this simply tells us the spine of our electrons. So you can either have -1/2, or you can have a +1/2 in terms of the spine. Okay, so it can either, an electron in an orbital can either face up or down. That's the spine quantum number. I hope people are clear, especially on how I was calculating the numbers for each. Okay, so for MS, it's always for you. You have to choose. You can either have -1/2 or +1/2. Okay, then for the N, you check the energy level. the subshell. Okay. Then here L tells you the type of the shape of the orbital. Okay. If it's 0, just know that it's the S. If it's 1, it's the P. D is 3. Okay. Then you can have F4, so on and so forth. Okay. So that's what we have. And now we are calculating L. We are using L is equal to n minus 1. Okay. Then for the ML, we are saying this is the orientation of the orbitals. Okay. So if we've given an example, if L is 3, we are going to have this orientation. So -3, -2, -1, plus 0, plus 1, plus 2, plus 3. That's what we have there. Okay. So those are types of quantum numbers, and we've talked about them here. Okay. Okay. So these are some of the examples in terms of the electrons. Okay. So here for the spine, we are simply saying we can either have positive or minus half there. We've already discussed that. And then these are the shapes of the orbitals you can have. Okay. So you have the 1s there. The 2s going to look like that. Then for the P, you can have the PX, PY, and the PZ. For the D, you can have the DXY, DXZ, DYZ, DX2, Y squared. Okay, then you can have the DZ squared. These are the shapes of orbitals that you can have. And you need to know how to draw these orbitals. You can be asked in a test and or an exam, especially the first two, the S and the P. The D and the F, these are very complicated. I don't think you can be, as these are 3D structures. So you can't be asked. But just in case you are asked, just make sure you know how to draw the shapes of these orbitals. Okay, we'll end here. Then okay, so we'll just end here. So let me do this. Just wait a minute. Okay.